This chapter is all about vectors. Vectors are a part of mathematics that have a lot of applications. You'll see them a lot if you take a physics class, or if you take linear algebra, you'll revisit vectors in more detail as well. So this is one of those things that gets used quite a bit, and we'll also use them pretty heavily in Calculus 3. So the first thing that you need to understand is the difference between a scalar and a vector. Any quantity which can be expressed by a single real number with units is called a scalar. So examples would be like area, volume, temperature, mass, time, etc. And scalar quantities have a scalar number associated with each one. Now some quantities such as force, velocity, acceleration, etc. cannot be represented by a scalar because they involve both direction and magnitude. And we represent these values with a directed line segment or a vector. So the vector v equals pq, and notice there's an arrow pointing from p to q that goes on top of that, has an initial point p and a terminal point q. The length or the magnitude is denoted by pq. Now whenever you type this, it tends to nest it, but usually it looks like this, where it's like two absolute value bars around the PQ. Now just a little note about vector variables. In print, you typically will see them written in bold font, which looks like this right here. That's how we differentiate the scalar v from the vector v. But in writing, we use some kind of notation to denote that this is a vector, either that arrow, or in some courses you'll see it written with this caret symbol, and that just means that it's a vector. So on your paper, when you're taking your exams, I do want you to be careful with that notation. Vectors can be written with lowercase boldface letters or with that arrow, and a vector technically represents a set of directed line segments, each having the same length and direction. So a directed line segment from P to Q, where P is the initial point and Q is the terminal point, and that order does matter. Equivalent directed line segments, you want to think of taking this arrow and picking it up and moving it, but not changing its direction or its slope. Two vectors are equivalent if they have the same magnitude and direction. Notice we don't use the word equal, we use the word equivalent. So two vectors are considered to be equivalent. If we let u be represented by the directed line segment from 0, 0 to 3, 2, and v by the directed line segment from 1, 2 to 4, 4, we're going to show that they're equivalent. So u is going to go from 0, 0 to 3, 2, and v is going to go from 1, 2 to 4, 4. So I'm going to show that their magnitude is the same, and I'm going to show that their direction is the same. So for u, we'll let this be p and let this be q. So the magnitude in both cases is the distance from p to q. And remember, the distance formula is the square root of x2 minus x1 squared plus y2 minus y1 squared. So for u, the magnitude of u will be the square root of 3 minus 0 squared plus 2 minus 0 squared, which is the square root of 3 squared plus 2 squared, or the square root of 13. V has a magnitude of the square root of 4 minus 1 squared plus 4 minus 2 squared. So that's the square root of 3 squared plus 2 squared, which is also the square root of 13. So these are equal, and that checks out. If you got two different values, you could stop there. You wouldn't have to go any further. Now when we're looking at the direction, we can just find the slope, which is y2 minus y1 over x2 minus x1. So the direction for u, and we'll call it m sub u, is 2 minus 0 over 3 minus 0, or 2/3. And for v, that is 4 minus 2 over 4 minus 1, or 2/3. So again, they are equal. So we can say U and V, and my arrow didn't quite come out here, so we'll rewrite that, are equivalent. There you go. The most convenient method for representing a vector is the directed line segment whose initial point is the origin. This is called the standard position. So we take that vector and we pick it up and we make P be 0, 0, and Q is whatever it would need to be relative to that. So notice that an ordered pair is written with parentheses and scalars. A vector is written with these angle brackets instead of ordered pairs. So a vector instead of parentheses. So a vector in standard position is written with those angle brackets, and it would be V1, V2, where those are the coordinates of Q. So this represents the point, whereas this represents the line segment V. And if you want to find those points, basically, we know that two vectors are equivalent if and only if U1 equals V1 and U2 equals V2. If we want to convert to an equivalent vector in standard form, all you have to do is subtract, but the order matters because you want to take the terminal point and subtract the initial point from it. So V1, V2 would be Q1 minus P1 and Q2 minus P2. From the distance formula, you can see if it is in standard form, you get the square root of V1 squared plus V2 squared, because basically it would be V1 minus 0 squared plus V2 minus 0 squared. Another word for the length here is the norm. That's a more general term for magnitude that you may see in some other classes or textbooks. Some special cases, if the magnitude of V equals 1, then V is called a unit vector. And the magnitude of V is equal to 0 if and only if V is the 0 vector. Now another thing that I want to be careful with, the 0 vector is not equal to the number 0. The 0 vector is specifically the vector with the coordinates 0, 0 for its terminal point. This example says write the following vectors in component form and find their magnitude. So we've got an initial point P, which is 2, 0, a terminal point Q, which is 5, 5. So V is going to be angle bracket 5 minus 2, subtract the x components, 5 minus 0, subtract the y's. So we get 3, 5. The magnitude is the square root of 3 squared plus 5 squared, which is the square root of 9 plus 25, or the square root of 34. Now you don't have to, but you can absolutely graph this and just show yourself that they're the same. So V as it's written would go from 0, 0 to 3, 5, which would look like this. Whereas P and Q, P is 2, 0, and Q is 5, 5. This is the vector from P to Q. They're equivalent. So you can see that they do have the same length and they do have the same direction. The next one we have 6, 2 and 6, 6. So V is going to be 6 minus 6, and we do want angle brackets, and 6 minus 2. So that is 0, 4. And the magnitude is the square root of 0 squared plus 4 squared, which is the square root of 16, or 4. This example says if V equals 2, 6 and V equals PQ, find Q when P equals negative 1, 4. Well, we know that Q is going to be some Q1, Q2, and we know that V1 has to equal Q1 minus P1. So that tells me 2 has to equal Q1 minus negative 1. So 2 equals Q1 plus 1, and Q1 equals 1. We know that V2 equals Q2 minus P2. So 6 equals Q2 minus 4, which tells me that 10 is equal to Q2 if I add both together. So I get that Q is the point 1, 10. If we have two vectors u and v, and c is a scalar, the vector sum of u and v is the vector u plus v equals u1 plus v1, u2 plus v2. So you add the first components and you add the second components. The scalar multiple of c and u is the vector c times u, which is cu1, cu2. So you just distribute the c over both components. The negative of v is the vector negative 1 times v, so both components get multiplied by a negative 1. And the difference of u and v is the same as u plus negative v, or u1 minus v1, u2 minus v2. A note about scalar multiples: if you look at this picture, and this is the vector v, you can see that if you multiply on the outside, it does change the magnitude, it changes the length by whatever that factor is. So multiplying by 1/2 halves it, multiplying by 2 doubles it. If you multiply by a negative, it also reverses the direction of the vector. Geometrically, the sum of two vectors is called the resultant vector. And if you take the two vectors u and v, wherever they happen to live, and you take the initial point of v and place it at the terminal point of u, like so, whatever the straight line from the initial point of u to the terminal point of v is your resultant vector u plus v. And that's what it'll look like geometrically. And you can see that if you were to do in the opposite direction v plus u, you would get a vector that is equivalent. Okay, so let's do some calculations here. It says v equals -3, 4, w equals 1, -3, and we want to find each of the following. I want to find first 1/3 w. So what I'm going to do is I'm going to take every piece of w and multiply it by 1/3. So that gives me 1/3 and -1. And that is my answer. For this one, I've got v minus w, so that's going to be -3 minus 1 and 4 minus -3. So that's -4 and 7. And for this one, I would have v, which is -3, 4, plus 2w, which is going to be 2 times 1, 2 times -3. So that is -3, 4 plus 2, -6. And then I have -3 plus 2 and 4 plus -6, which gives me -1, -2.